So I am Jean-Marc Colley, software engineer in a physics laboratory at Sorbonne University in Paris. So we'll start with short presentations of CPU and memory profiling tool for Python. Next, we will see the basic concept for calculation efficiently with Numpy and do some exercise. So let's start with PySpy. So PySpy is a profiler for Python. PySpy is sampling profiler. It lets you visualize what your Python program is spending time on without restarting the program and modify the code in any way. PySpy has three modes: dump for display the current call stack for each Python thread, top, see in a real time functions that taking the most time, and record for recording profile to the file with the option -O. So the command example to use PySpy is PySpy record output file, JSON output file, and some parameter in your Python program. At the end, you can visualize the result JSON in speed code website. Here you have some view. Yeah, like this. You see all your function, the time consuming, and so on. So this tool is provide the most consuming function, and when this function is identified, you can change the tool to profile it. It's a tool at function level. It's a lightweight to time the duration of function with timeInt module. timeInt function associates and defines the function to estimate function with a number of iterations and return the value of the total duration. They also function in IPython magic command %timeInt. So, example. So in my example, I profile the time of test cube function, and timeInt return the mean duration with a variation. And the duration is evaluated on 7,1 and 10,000 loops each. So it's the mean of the duration. Another profile tool is for memory. It's a tracemalloc module. It's a standard module in a Python library. It provides information about where objects are allocated, a statistic on allocated memory block by a file name and a line number. So to use it, you must add some instruction in your Python code. You must import the tracemalloc module and start the profiling. And at the end, you collect all information on your program. So in this example, you return the top 10 of the most consuming memory function. Another tool to profile memory is PSUtil. It's a powerful library to check memory allocation and running time on the current process, and PSUtil also gives information of CPU, disk, network consumption, and other information. So to obtain the memory occupation for the specific allocation in the code, you must invoke PSUtil and define object PSUtil process. And at the end, you have a structure where you have the result. The last tool for profiling memory is a memory profiler. It's a Python module to monitoring memory consumption of a process, as well as line-by-line analysis of memory consumption of a Python program. It's a pure module which depends on PSUtil tool. So to use it, you just add a decorator at profile. And to launch your program, you must use this line, Python and memory profiler, and the name of your script, Python script. And at the end, you have this output. At left, you have your line program, and I write your line program, and left the memory usage. So now we pass to the other course. So the Python course is available on this GitLab. I think you have the link in Discord. So actually, we are in a CPU directory tutorial. And now I present this one, Python and Numpy part 1. So I return to my Jupyter notebook. Voilà. So Numpy. Numpy is an essential Python library for scientific computing. It's made of more than 500 functions for fast operation on array, such as Fourier transform, linear algebra, a random generator, a math function. Numpy use a backend written in C++, Blas Laplace, which ensure SAMD vectorization. If we use it correctly, you can greatly improve the performance compared to the native Python. So we start with data structure of Numpy. There are 3 data structures. ND array, all elements of ND array for n-dimensional array, all elements have the same type, and the memory element is correctly done for SAMD vectorization. The other data structure is matrix vector. It's a sample 2D, 1D ND array. And another structure for Numpy is structured array. It's a set of ND array with column name, with a different type. It's a heterogeneous type. It's like a data frame in Panda. So now we will focus on the ND array data structure. It's a class. It's a central object of a Numpy library. The important attribute is a shape, return a tuple with the number of elements in each dimension or axis. D-type, Numpy defines its own type, like a float float 32, int 16, and so on. And another attribute is n bytes. It's the occupation of the array in memory, the size. Example of important methods, it's reshapes. Redefine the number of elements in each dimension. And in Numpy vocabulary, you use a dimension or axis. Another method is as type for conversion into another type. And you have a copy method to return the duplication of array. So here we have an example of creation with a simple list with the type. So here you see it's an integer, but I ask for float. So the type of the array is ND array, but is defined with Numpy array. And here you see the conversion in a float. There are other examples to create array with a Numpy function. You can initialize array with 0 with Numpy 0 function. In this function, the first parameter is the shape of the array. So 2 is a number of elements for axis 0, and 3 is a number of elements for axis 1. You have also Numpy 1. Your array is initialized with 1. Also Numpy empty. So you see a strange number. So it's what he finds in memory at this moment. It's not initialized. Maybe it's the allocation is more efficiency. And you have function to create array with suffix like, empty like, 0 like, and the first parameter is another array. And the function return array with the same shape and the same type as the array parameters. So in this example, I ask an array 1 like of AX, and AX have 2, 3, the shape is 2, 3, and the type is integer. So you see the return array have the same shape and same type. There are many other function allocation creation. You have a link here. So now I will remember some basic notion of slicing. Numpy uses the same slicing convention as Python. So the first index is 0. To define an interval 2 points 4, you have only two elements. So 4 is exclude. The upper limit is exclude. In math notation, you must see as this interval where 4 is exclude. Negative index is allowed. -1 is the last value. So my list have 10 elements, 0 to 9. So the last element is 9, okay. To have the two first elements, the syntax is 2.2, returns the two first elements. To have the two last elements, it's a minus 2 point, and you have 8 and 9. To have all elements, it's simply 2 points. Okay. Oops. Now I will speak about broadcasting. Broadcasting is the central concept of Numpy. It's allowing you to avoid writing a Python loop. The emblematic example of the emblematic example is the multiplication of array by a scalar. So you define a basic array, define B as a scalar, and the NumPy multiply all elements of array by 2. The syntax is clear. It's also very fast because the loop is performed outside Python. Here you have a broadcasting representation. So here you have your array with 3 elements, and B you can represent it as array stretch in the direction of the other array to apply element by element the multiplication. The concept can be extended to the higher dimension number. For example, with a 1-dimension array and a 2-dimension array, if the number of 1D array match with the number of 2D array column. So in this case, broadcasting stretch the vector in this direction and apply a term-per-term operation. So we can define the constraint to use broadcasting. NumPy compares the dimension of 2 arrays starting to the right. After there are compatibility constraints. If the dimensions are equal, no problem. If one of the dimensions is 1, it's a stretch to match to other, like in this figure. Otherwise, NumPy raise an error. Now you will see an example where the broadcasting is not obvious. So the use case is a multiplication of array of an image by a calibration scalar, but specific to each image. So it's a vector with the same number of images. The choice of the shape for array is this one. So first dimension is the number of images. Second dimension is the number of rows. And the last dimension is column. And the calibration vectors is n, like the number like a number of images. So you can define image with a random function with the good shape. So I do a random function between 0 and 1, and we shape it as C below. So 10, 200, 300. Same thing for the vector coefficients. And if you want to multiply coefficient by image, you have this error. So operating could not be broadcast together with shape 10 10, 200, and so on. Let's compare the dimension of the two arrays starting from the right. So the vector image is here. Oops. And the vector of calibration is here. So 10 is compared to 300. This is NUC. So what should we do? First solution, we can return to the scalar multiplication array with Python oops. Or you can use broadcasting, but it's required to modify the shape of array. So we have two solutions. You can modify the shape of the array. You can modify the shape of the image. You must put 10 to the right. So here is actually the actually shape of the image array. So you must put 10 on the right. The second, you can modify the shape of coefficient by adding two dimensions to have 10 at the same rank of 10 of the image. So you must answer dimension with one element. And in this case, the broadcasting is OK. So now we will see the axis manipulation to modify the shape of the array image. We have a free function to modify the order of the dimension. Transpose, so it reverse the order of the shape. So in this case, we put 10 at right and 200 at left. Swap axis, you choose two axes and you swap it. And the last function is move axis with two parameters. So insert the first parameter into the rank of the indicated by the second this parameter, and shift the axis to left. So for example, to move axis on image 0 for the first index and 2 for the target dimension. So actually, axis 2 is 10, and you put 10 at the end. And you shift to the left the other dimension. We will write a solution 2 with a swap axis in an outplace version. In fact, the result is in a copy array. We use a suffix underscore OP to name the function OP for outplace. And the result must have the same shape of the input array, so you need to apply swap axis 2 times. So I define the function. So I apply swap axis 1 time. I can multiply by coefficient, so the broadcasting is OK. And to return to the initial shape, you must apply a second swap axis. Voilà. Now we will see the solution 3, where you must add empty dimension. So here you have a figure with a 1D array A and a 2D array. In fact, it's legitimate to be able to consider a 1D array like A as a 2D array with a single row. This point of view, it doesn't require introducing additional data. With NumPy, this is possible with the notion of new axis, which increase in the array by one dimension with a single element. NumPy extending dimension do the same thing, but with a functional approach. So here, an example, I have my array 1D as a line, and I insert a new dimension with NumPy dot new axis, and ask the shape of this new array, and you see a dimension appear with one element. So we will write the solution tree with this feature. So from shape 10 for coefficient vector to 10, 1, 1, you need to apply 2 times new axis at right. Introduce a new notation for a new axis. You can replace it by none. It's a shorter way to invoke a new axis. So the solution tree is right here. So you multiply coef with all elements and answer none, two empty dimension, and multiply by image. So in this case, the broadcasting conditions are satisfied. So execute this function. As you see, it's also the same time for the swap solution. 280 microseconds and 270 microseconds. It's equivalent. But the solution tree with new axis is the solution you see the most of the time, because the syntax is very short and clear. So now we will do the validation of broadcasting with the different solution. So we will define a reference version with Python loops. It's solution 1 called naive solution, where you start by a copy. It's an outplace version. You start by a copy of your array, image array, and the multiplication of each line of array is performed by Python loops, where the broadcasting scalar is okay, and return the copy of array. So I time it this function. You see you have a factor 2 for the broadcasting version. So Python loops is 2 times slower than broadcasting in this case. Now we will check if the results are the same for all methods. So NumPy provides a function called allClose, which compare term by term all elements of an array. So I call the free function, and I compare the broadcasting solution to the reference implementation with Python loops, and allclose return a boolean. So it's a true or false. Here you have no parameters, but you can fix relative error, absolute error, the threshold of the close notion. So here all is okay. Now some words on broadcasting limitation. You can find this warning in Numpy documentation about memory consumption of broadcasting. In some cases, the memory consumption can be very high. And in this case, the documentation say it's better to write the algorithm with Python loops. Next course, Alice will speak about Numpy library, and Numpy library is certainly the good solution for this case. So keep in mind this warning with broadcasting, and your benchmark must be realistic. Will do with realistic data size to avoid scanning issue. Now we will speak about another important notion in scientific computing is in-place processing. The in-place processing are performed over the data in array, and the result are stored in the same array. With in-place processing, you save time by not require memory allocation. It's an important concept in the optimization. Some program spend time to allocated is allocated, allocated is allocated, and the use of in-place concept is very useful to improve your program. So some basic reminder with Python where you write B equal A. B, it's a reference of A. It's not a copy. It's a Python feature. And when you define this array from NumPy array A as only the first line, so line 0 and all value in the column. The line, it's an example of view of array A. It's not there are no copy of data, and it's a NumPy feature. So there are no duplication memory with to define a variable line. Function, NumPy function on transpose, move axis, swap axis, return a view of array for recent NumPy version. So you can do broadcasting with this view if necessary. There are also the classic in-place arithmetic notation, plus equal, minus equal, multiply equal, and so on. And at least most of element-wise NumPy function have a parameter out to perform processing in place. So example with sinus. If you want to put the result of sinus in the same array as angle, you just add the parameter out equal a as the input parameters. So now you can rewrite the function, the solution of image multiply coef with this approach in place. So for this function, I use a suffix underscore IP for in place. So for the naive solution with Python loops, it's the same function without the first line copy. There's no return function. Remember the first outplace, you start with a copy and return this copy. In the in-place version, there are no copy and no return. For swap axes, so you start by define a view of image with a swap axis, and the array return is a view, and you can multiply by coef. In fact, the result is in a variable image. So no return, because you use in-place operator multiplication. For new axis solution, is very short, one line. So you use the in-place operator multiplication and just add additional dimension to the coef array. No return function. The result is in input array. So you can compare the operation in place. So we start by do a copy of the image, because when you apply the in-place function, this variable will modify. So as you see, there are no return for swap axis underscore IP, and check with allclose that the results are the same for the reference function outplace. So the return of allclose function is true. And in this case, you compare the output of naive solution outplace, and for in-place version, you use the input array to check the result. To evaluate the time of in-place function, it can be tricky, because the output array is the input array. So you define like suite series. It can be diverged quickly. So you must limit the repetition of time int and the size of the loop. we have two options for this, dash R and dash N. So now you can do the time int with small value of repeat and size loop, and you obtain this number, 150 microseconds, to compare at 90 seconds. So you have almost factor 2. Factor 2 without copy. Now I will speak about reduction and implicit loop. So a reduction is an operation that summarizes several values into one, like sum, average, max. Numpy implements this mechanism to iterate through elements to avoid writing a loop with the axis parameters. So when you define a reduction function with axis equal n, you indicate to the function that the reduction loop is along this axis, and the return array, the size along this axis become 1. By default, this axis is squares. Return array, the return array lose this axis. But you can keep it with parameter keep dimension equal true to prevent this. Example, you define a sample array with 2 lines. You want to compute the sum on on axis 1. So in the first version, without keep dims, the function return an array with this shape. So it's a sum along all line. And with parameter keep dim, you have 2D array, like the input array. Another area where NumPy provides functionality to avoid writing Python loops, it's selecting element from an array to make another array. We have 2 ways: the fancy indexing and NumPy function take colon axis. There are another one. I don't remember the name. There are another NumPy function to select elements. So with fancy indexing, you can put an array, an index array, 1 or 2D, or list between a bracket of array. Example, to collect the maximum of each line for AA array. So the max of the first line is 2, the max of the second line is 5. Donc to select this element, you can write this line. You see you have a first array. It's an index for axis 1. And this array, it's an index for axis, no, the first is array for axis 0, and the second is array for axis 1. So here, to select the first maximum of the line, it's line 0, colon 2, it's 2. And for the second line, it's line 1 and also colon 2. So return the max of AA array. It's possible to write this. More appropriate for larger array, you can use take all on axis. And this function, it's compatible with the output of argument arg family function, like argmax, argmin, argwhere. So here the first function search the argument of maximum in your array. And you use, in this case, the parameter keep dimension. And in this case, you can apply directly the output of argmax in a function take all on axis. And the result is here. It's a 2D array with a maximum for the first line and second. So when you have a very big array, this way to select elements is very fast compared to the Python loops. So conclusion, we have seen the two important concepts of Numpy to obtain a good performance. Implicit loop with broadcasting, reduction function, selection function, and also the in-place processing with view array, output parameter of most of Numpy function, and classic operator in place plus equal family. So now, if you have a question, you can ask it. And after we will, I propose you some exercise. So the first exercise is very simple. It's a slicing exercise. Very easy, I think. The second one is an exercise about broadcasting array 2D, 1D, and calculation in place. After you have exercise on in-place version of sinus AX plus B. And the last, it's optimization of the max function. So I think the first exercise is very easy, and the last is hard, more harder.
I have a question. So I've just done the exercise 2 when you are comparing a for loop with the broadcasting between 2D and 1D array, and I have like a speed up which is 5 order of magnitude, while in the beginning of the course with the broadcasting on the 3D array, it was like a speed up of about 30%. And I wanted to know why you have such difference in the speed up when using broadcasting between these two cases.
Sorry, can you repeat, please?
Just I wanted to compare the
Yeah.
speedup by using broadcasting between the for loop in Python.
Yes.
And in the first case of the course, when you presented that, we had an improvement of about 30%, while in the exercise 2, I have a speedup of 5 order of magnitudes. And I wanted to understand why we have such a speedup in the second case and why not in the first one.
The broadcasting is applied on more elements.
Yeah, but for the first one, I tried with a very, very huge 3D matrix, which was about 20 giga, so it was very huge, and it was not significant, the speedup. So, and it was a 3D array, while in the second exercise, it's only a 2D, so it's smaller as well. So I'm a bit surprised by that.
In fact, I think the speedup is proportional to the number of elements that broadcasting manipulate. I think is the explication.
Yeah, but in the first example, you have an array which is 300 times 200 times 10, and the last one it's like 50. Yeah, okay, no, it's 50,000, I think. Okay, so maybe that's explanation. Yeah. Okay. Okay, thank you.
So for the second exercise, you must write four functions. Like in the course, you can use broadcast with modifies to array for outplace case and in-place case. So if you need help, I can. Everybody find the solution for the first exercise? Yes? So the good answer is this one. You must use a slicing feature with a negative index to extract the sub-array in a tab array. So 9 start to the 0, 1, 2 lines is here, and the colon is 1, 0, 1. And 10 is to rank by the end, so you got -2. And the colon is the first. And as the second index is excluded, it's a 1 in this case. So here you have the solution of the first way to do the broadcasting with a new axis. it's simply to add dimension to V and add to A. For the second, don't use swap axis, but the transpose feature to just A transpose plus V. But I think it needs a transpose to have the good shape in return. So now you can find the solution for the in-place case. If you have question here or on a satellite site, don't hesitate to ask me. Now the solution for in-place version. So with new axis, it's very short. You use the in-place arithmetic plus equal, and you add a dimension to V. No return. And for with transpose, you start to transpose the array, and so it's a AT, it's a view, and you can add it to V, and the result is in fact in the array A. So it's a view, it's the same memory space. So you can adapt for swap axis. How many speedup you see in your computer between in-place outplace loop version and in-place broadcast version? Factor 10, 2. No speed up. Someone find the solution? So now exercise 3. It's a version in place of sinus AX plus B, where A, B are scalar, and X is angle. It's a big array. The first implementation of this function is here. And I propose to you to write the in-place version. So the result of the function will be in X variable. So the solution is it's first to multiplication to A with in-place arithmetic multiply equal. After you add B, and finally you use a sinus with output parameter as X. So with the solution, you gain a factor 2. Now we check if the result is the same. So the order of call of function is important because the second function is in place. So I compare R1 with X. It's true. So this in-place version of sinus is 2 times faster than out-place version. So I think the time is finished. Thank you. So it's a tea break, coffee break. You return to 11? 11.